in a little bit.
I love that.
So welcome back to Mr. Strauss's Chemistry Corner. I know it's been a while. To my friends in Poland, Przepraszam, and my friends in Germany, Guten Tag. We're going to go through the test. No animals were hurt during the filming, and this is recorded before a live studio audience. All right. So let's go through the answers to the test. Number one is A, pressure is force divided by area. Number two, the energy required to change 1 gram of a solid to a liquid is C, enthalpy of fusion. Number three, a volatile substance will evaporate quickly. So A, if it has a high surface tension, it would mean it would have strong intermolecular forces. But if it's evaporating quickly, it can't have high, if it's evaporating quickly, it would mean that the bonds are very strong and therefore would have high surface tension. So it can't be B because a volatile substance evaporates quickly. And it can't be C because if you had strong intermolecular bonds, then you wouldn't evaporate quickly and therefore you wouldn't be a volatile substance. All right, figure 1. What's the triple point? In figure 1, the triple point is letter H, right in the middle. There's your triple point. What is the phase at point B? Well, this is solid. This is liquid. This is gas. So even though point B is way down here, you are still a gas at that phase. So B is gas. What happens when you go beyond the critical point? Letter I is the critical point. If you go beyond that, you're not a liquid, you're not a gas, you are a superfluid. So when you go beyond that point, the density of the liquid and the gas are equal. Letter D. At 250 ATM, what's the boiling point? This is the freezing line. This is the boiling line. So when you're on that line, you are boiling. At 250 ATM, you would boil at about 125 Kelvin. So the answer is 125. Where are you sublimating? This line is the sublimation curve. So on letter G, you are going to be sublimating. Where is the critical temperature? This is the critical point. The critical temperature will be somewhere again around 130 Kelvin. Or you might have put point I. So either one, point I or 130 Kelvin. So on the retake, you'll have a graph like this again. Obviously, it's not going to be the same identical graph. The idea is that I'm testing your skills, not your memorization ability. So you'd have a different graph, different points. Questions? You want to make sure you understand this so that if you're going to retake it, figure 2. Where does melting begin? So in this section, you're heating your solid, and your solid's getting warmer and warmer and warmer and warmer and warmer. When you hit point A, that's when the melting begins. You start to melt at point A. So that's 5A. what is the numerical freezing point? Well, the freezing point and the melting point are the same, right? When does water freeze? At 0 degrees Celsius. When does ice melt? At 0 degrees Celsius. If you're doing Fahrenheit, when does water freeze? 32 Fahrenheit. When does ice melt? When the temperature reaches 32 Fahrenheit. So this plateau is the melting point and the freezing point, and so that's about 125 Celsius. So where is their liquid going to be present? And this one was worth 3 points. If you're beginning to melt here, there must be liquid in section 2 because you're melting. In section 3, you've got liquid. And in section 4, that's when you begin to boil. Well, if you're starting to boil, you must have some liquid. So in these 3 sections, you have liquid. Okay? Here you're a solid, here there's some solid, it's melting. By the time you get to point B, all the solid is gone. Here's where you begin to boil. By the time you get to point D, all of your liquid is gone, and in section 5, all you have left is gas. Now for the fun stuff. Manometer problems. Ooh, let's see. Christoph, could you read number 6?
Christoph?
You are now.
Okay. A closed manometer is connected to a container of neon gas. The difference in the height of the mercury in the 2 arms is 517.5 millimeters. What is the pressure in kPa?
Okay, closed manometer. It's, with a closed manometer, the height difference is always higher in the closed end arm. The height difference is 517.5. The pressure is just the height difference. That's the pressure. So all you have to do is convert to kPa. That divided by that. We've got 3 sig figs, 6 sig figs, 4 sig figs, so our answer will have 3 sig figs. It'd be 69.0 kPa. And if I made a mistake on your test, just let me know. I can give you the points at the end. Number 7, we've got an open manometer. With the open manometer, we have to do a little bit of thinking. You've got the air pushing down, and the pressure of the atmosphere is 97.2 kPa. Then you've got the gas pushing, and you have to figure out which one's stronger. Well, what are the heights of the liquid? It says that it is 180 millimeters higher in this side. So if it's 180 millimeters higher on this side, then who's stronger, Ian, the gas or the atmosphere? The gas, because it's pushing the mercury up into that side. So if the gas is stronger, you're going to add the height difference. So we would do 97.2 plus the height difference, But of course, Pashemik, the units have to be the same. So that means I have to convert. All these conversions are on your appendices. Three sig figs, 5 sig figs, no, that's 6. 3, 6, 3, and 3, so we round our answer to 3. So the pressure of the gas is 121 kPa. The conversions, you guys, I think everybody got these right. All you got to add is, for letter A, negative 20 plus 273 gives me 253 Kelvin. For letter B, we got 450 Kelvin, so I'm going to subtract 273 to get to Celsius. And we've got 0 Kelvin, so minus 273 to get the Celsius. So any questions on that page before I go to the next one? Oh, we still have to do number 8. So number 8 was worth 11 points. When you see a problem that's worth a lot of points, you should think there's a lot involved. And so, how much energy does it take to turn 10 grams of water into 35 grams of steam? So, here's our starting point. It's at 35 degrees Celsius. How hot can you get water? Can you have a glass of 60-degree water? 70? 80? What happens when you hit 100?
Starts to evaporate.
Starts to boil.
Oh, yeah.
So you can't get higher than 100. And that's your final, that's your initial when it comes to section number 1. So in section number 1, you have M delta T Cp of water. The mass is 10 grams. Specific heat of water is 4.184. But this is where most people made the mistake. The final temperature is 100. The initial temperature is 35. So when I plug it in, final minus initial, when I do this subtraction, I end up with 65. 65 is 2 sig figs. That is 3 sig figs. That is 4. So I'll round my answer to 2 sig figs. Yeah, you can go. You got it. Okay. Thanks for asking. So there's our answer in joules. But we're not done yet. All we did was heat the water up. So you put a pot of water on the stove, Connor. You gotta heat the water first. It doesn't just start boiling. So you gotta raise it up to 100. Once it hits 100, then it starts to boil. You get that plateau. We're boiling. That's section 2. Now you use a different equation. Q is equal to mass times the delta H of vaporization. Our mass is 10 grams. Delta H of vaporization is 2,260 joules per gram. That's the amount of energy it takes to boil. But we're not done yet, Igor. Because they want to take that boiled water and they want to raise the heat of it to 175. So here I'm at 100, here I'm at 175. Here we're going to heat the gas. Screen close up. So Q is equal to M delta T Cp, but now the Cp is for steam. Specific heat of steam is 2.06. The final temperature is 175. Our initial temperature is 30, not 35. The initial temperature is 100 because we're just doing it for this section. So 100, the mass stays the same. So we've got Q is 10 times 175 minus 100 times 2.06.
Isn't it 2.02 now?
Whoops. Yes, you are correct.
Don't forget our point.
Oh, I won't forget. I'll put those mistakes up there. So this comes out to be with 2 sig figs, 750 joules. Two to go. Then you just add up the 3 numbers. We've got this one, and this one. So we add them up. Yeah, I knew I did something wrong here. This number didn't look right. I added instead of multiplying. That should be 75 times 10. That's 1550. There we go. Add those up. $26,800 joules is the final answer. That's the amount of energy it takes to go from 35-degree water, all the way up to 175-degree steam. So again, on the retake, I probably won't ask you to go through all 5 sections from like raising the solid all the way up to steam. Like I said, I probably won't make you calculate all the way, but I'll pick a point on here and have you calculate a couple sections of it. So you need to know where you are on your graph. Any questions on 8? All right, let's see, could you read number 9 for us, Blair?
An internal combustion engine in a car operates by injecting fuel, vapor, and air into a cylinder, compressing the gas with a piston, and igniting the pressurized gas. Suppose an engine cylinder has a volume of 0.420 liters when the gas is injected. The gas has a temperature of 32 degrees Celsius and a pressure of 92.0 kPa. At the time of firing, the piston has compressed the gas and the cylinder volume is now 0.0494 liters, and the gas is at a temperature of 400 degrees Celsius. What is the pressure of the gas at this time?
So this is how your car works, Danielle. You've got this area here called your cylinder. You open up a little valve, in comes the gasoline. You open up the other valve, in comes the oxygen from the outside. Then the piston compresses it. The piston goes up and squishes it into a small little area. Then the spark plug ignites it, and when it ignites the gasoline and the oxygen, it explodes, pushing the piston down. And when the piston is pushed down like that, it spins around, and as it spins around, it turns the crankshaft, which then turns the wheels. Okay? So it all starts with filling that little chamber with gasoline and oxygen. So in number 9, the initial volume is 0.420 liters. The initial temperature is 32 degrees Celsius. The initial pressure is 92 kPa, close to atmospheric. Then you compress the volume to a tiny little area. The temperature is higher. And we want to know what the new pressure is. So we need an equation that has V1, T1, P1, V2, T2, and P2. There's only one equation that has that. And that's the combined gas law. Celsius always has to be in Kelvin. So some people had trouble with that. Make sure your temperature is always in Kelvin. Then we do the algebra. So we need to get P2 by itself. And the fastest way to do this is multiply by T2 over P2. Because then the P2's cancel, the T2's cancel, and then I'd be left with T1 T2 times P1 times V1 over P2 times T1 is equal to, we want P2. It's a good thing I teach this stuff. Sorry about that, DJ. So we want P2 by itself, so we're going to do this. So the V2 and the T2 cancel. Then we get T2 P1 V1 over V2 T1 is equal to P2. Much better, don't you think, Malgorzata? All right, let's plug the numbers in. T2, 673 Kelvin, is P1 times V1 divided by and if we do our math right, it'll come out to be 1,730 kPa. Kelvins will cancel, liters will cancel, the only thing left will be kPa.
One of the Calvin is wrong. Is it the same thing?
Whoops. Ooh. Wow. T1 should be 305. Yes, it is. So, again, that's why we write everything down, because it's very easy to see I wrote the wrong one, right? But if you don't do that, it becomes harder to tell. Okay, number 10. Maintaining constant pressure, the volume is increased from 15 cubic decimeters to a volume of 35 cubic decimeters. The initial temperature is 20 Celsius. Celsius must always be in Kelvin, so I just went ahead and converted it right away. You want to find T2. First, let me show you the wrong way to do it, and then I'll show you the right way. I saw a lot of this. We're trying to solve for T2. So what some people did, the first step was right. They divided by V2. And so you divided this side by V2. And they got this.
Thanks.
But where's the T2? It's in the
Bottom.
bottom.
You have to
So
put
if you
one
do
over.
this, that's okay algebraically, but the T2 is still in the bottom. This is algebraically correct. What some of you did was you got to this point and then you magically elevated the T2.
That's because in algebra we were just told to assume there's a 1 there.
You can assume there's a 1 there, but it's still, I mean, throw a number in. Is 1 over 4 the same thing as 4?
No.
No. And 1 over T2 is not the same as T2. So the fastest way to do this correctly is this a true statement?
Yeah.
If I flip it and invert it, is that still true? This means tak. This means nia. Okay? Tak. So the easiest thing is to take these and flip them. So it becomes this. Now we've got the T2 in the numerator. So then all I have to do is multiply both sides by V2. So I end up with V2 T1 over V1 is equal to T2. So that's the fastest way to isolate the T2. Then we can plug in the numbers. 35 times 293 over 15. And T2 will equal 684. And for those of you who did your algebra wrong, I hope you were thinking about your answer, because my volume got bigger. What's the relationship between temperature and volume? If volume gets bigger, if temperature gets bigger, volume should get bigger, right? If temperature goes up, volume should go up. So my volume went up, that means my temperature should be higher, right? It's that increase of temperature that caused the volume to get bigger. All right, 11 and 12 are a little tricky. All right. For number 11, it says we're collecting 96 cubic centimeters of gas over water at a temperature of 27 degrees Celsius. The pressure is 122. We want to know what the dry gas would occupy at a new pressure of 127 and a new temperature of 70 Celsius. Now when you collect the gas over water, so here's my sink, here's my flask. When you collect the gas over water, you don't just have your gas in there, you also have water vapor. So when they say the pressure is 122 kPa, that's not the pressure, that's the total pressure in there. We have to subtract out, Nick, the water vapor pressure. That's why you go to Appendix O. Our T1's 27 degrees Celsius. So you go to Appendix O, and at 27 degrees Celsius, the pressure is 3.6. So we have to subtract out 3.6 to get our P1. So now we've got V1, T1, P1. We've got P2, we've got T2. We're trying to find V2. We will use the combined gas law. Multiply both sides by T2 over P2. That cancels. So we're left with this. Okay. Now we can plug in our numbers. If I went too fast, what you can do, Agnieszka, is just watch this over and over again on YouTube. You can slow it down. So T2. Oh, it's got to be in Kelvin, right? So we got to add 273. So that would be 343 in Kelvin. So 343 times P1 times V1 divided by P2. P2 is the 107 kPa. T1, have to add the 273.
It's hard to voltage.
That's 300 Kelvin. So 343. Final answer is, really I should have 3 sig figs, not 4. So the final answer is 102 kPa. And yeah, that's a little tricky one. It's a lot of work there. The last problem is the same thing, just different gas law. And go to number 12. We're collecting 372 milliliters of gas. Our T1 is 90 degrees Celsius. Our P1 is 111. We're going to standard pressure, which is 101.325. So you needed to know what standard pressure was. We're starting at this pressure, we're going to P2, and then we're going to find V2. We're collecting over water, so just like in the last problem, we have to subtract out the water vapor pressure. So Shustov, we have to go to Appendix O. And at 90 degrees Celsius, the vapor pressure is 70.1. Okay, so at 90 degrees Celsius, the vapor pressure is 70.1. So we have to subtract that to get our real P1. And then we're set to go. Temperature is staying constant there, Connor, so we don't have to worry about it. P1, V1, P2, V2. Solve for V2. Plug in the numbers. So P2 is, P1 is 40.9 times V1 divided by P2. And the V2 is 150 kPa. Yep,
It's a volume, how could it be kPa?
can't be. Got to be.
You did the same thing on problem 11 too.
I did.
Yeah, you did.
And so,
We broke 1,000. kPa.
We need those horns.
Milliliters,
Centimeters cubed.
oh,
Fucking
centimeters
school
cubed. That one should be milliliters. So we get those mistakes up here. That puts us at 100, 1,000,
like
two.
right at 1,000.
And then, if I made a mistake in your test, let me know, I'll fix it. Otherwise, we've come to the end of another episode of the Chemistry Corner. So now we can sing our ending song.
Thank God.
Good night, sweetheart. Well, it's time to go. Boom, 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 boom. There we go.
Don't add on to it. Okay. I just had 1, 2, 3. Watch this. Watch this.
I'm watching.
I got another hour today. So I got 3 hours in 1 day. Watch this. That's really loud, Dada.
That's really loud.